Hi, I'm Chris Su. I work on the CoreOS team here at Microsoft, and today I'm going to talk about OpenHCL, the new open source Paravisor. Before I talk about OpenHCL and what is a Paravisor and why is it useful, I want to just level set a little bit and give some background on confidential VMs in general. I know most of us here probably already understand why confidential computing is valuable and why we want to use it, but it's good to give a little bit of background just so that we can understand more about why OpenHCL is so useful. So what is a confidential VM? Here, confidential VM we're defining as a VM that is using hardware-based memory encryption to secure guest workloads at runtime. So these are technologies like AMD SEV SMP, Intel TDX, ARM CCA, and these all provide a mechanism to run a guest that has its state fully encrypted from the host, so the host can't access it. Additionally, a confidential VM, we can attest the state of the guest before releasing secrets to that guest, right? This is done via launch attestation, etc. So why would we want to use a CVM? Mainly to get these new security guarantees for the guest, right? We want to protect as much state as we can from the guest and the guest workload from introspection or tampering from the host, and previously we were unable to do that. In the next few slides, I'll show more about what does a traditional VM look like and what does a confidential VM look like, and what different components are getting protected. And because of this additional protection, we can minimize the software trusted computing base, or TCB, and really limit the things that a guest and guest workload need to trust, right? We're removing the host OS, we're removing the hypervisor, and anything that could be running on the host OS. And because we can attest the state of this smaller TCB, we know that when we release guest secrets to the guest workload, the guest is in a known good state. So here's a picture of a traditional VM. We have the guest OS and the host OS. Here you can see all the different components in a guest OS and host OS, and we have a hypervisor that manages these two different virtual machines that's running on top of hardware. But crucially, because it's not a confidential VM, there's no protection between the host introspecting guest state. This is how traditionally virtualization stack can offer virtual machines by modifying guest state, doing direct memory access, etc., so that we can emulate these different devices and allow the guest virtual machine to communicate with the host and other components. In a confidential VM, the model is different, right? The contents of the guest and the guest state are protected by the hardware, so the host OS is unable to access any of it. So here, you can see that we've drawn this box around the guest OS, and the guest virtual machine, where the host is unable to read or access state inside the guest OS. So, we can't run emulated devices, we can't do direct DMA, and so we have to put those things somewhere else. Like if we want to offer a TPM, it needs to be offered within the guest with this thing we call Paravisor. And you can see how much we can shrink the trust base of the guest as well. The guest no longer needs to trust, the whole host OS, the hypervisor. It just needs to trust its own OS, which it had to trust before. And now this smaller component we're calling the guest Paravisor. So what is this Paravisor thing that we talked about before? It's a firmware component that runs inside the guest at a higher privilege level. To be specific, on, let's say, AMD SMP, this is VMPL0, and on TX with partitioning, this is the L1. And this higher privilege level allows us to provide different emulation for unenlightened guests, provide various services like interrupt virtualization, and also provide additional security for the guest, because you can think of it as the Paravisor is really the root of security for the guest. It's running in a high privilege level. It has access to everything within the guest, and it can interpose itself between communications with the guest OS and the outside world. So why would we want to have a Paravisor? Well, the biggest reason is that we want to be able to run other guests like Windows or Linux. Newer Linux distros have the ability to run what we call fully enlightened within a confidential VM. That means that they have the correct changes to interrupts. They understand the architecture. They understand memory acceptance and memory encryption, so that the guest doesn't need a Paravisor or some entity to run correctly in this environment. But a lot of these things are pretty invasive to the guest OS, right? To do interrupts correctly requires a lot of pretty specialized code that is pretty hard to retrofit into older operating systems. So you can use a Paravisor to provide, interrupt virtualization, filter devices that may not have fully hardened drivers in the guest. A lot of drivers traditionally trust that the hardware is not malicious, right? And we can also use the Paravisor to host other emulated devices, like a virtual TPM, serial for a console if we don't have some kind of enlightened console. And we can do things like, well, I'm running an older guest OS that doesn't understand NVMe, but now I can translate NVMe storage to some other kind of storage, like a paravirtualized storage, in our case, VM bus, or you could even go something like an emulated storage device like IDE or something like that. And because we have this additional environment, we can do attestation in the Paravisor. We can provide additional guest diagnostics that without modifying our existing guest OS. So previously at OC3, some of my colleagues presented on Microsoft's first Paravisor. We talked about confidential computing and how Azure thinks about confidential computing. And we had this first Paravisor, which we wrote in C and C++. I did interrupt virtualization so we could run Windows and older Linux distros. We provided a VTPM. We did attestation. But the big thing is this was a closed source project. And we've gotten a lot of feedback from partners that they really want to see, because the Paravisor is such a crucial part of the security of your guests, they want to see all the source code in the guest, which is reasonable, right? You want everything in your TCP to be transparent. You want to trust that what you're running in your confidential VM is what you expect. So with that, we thought a lot about, okay, what's the best way to have an open source Paravisor, right? And we also thought a lot about how do we want to evolve. What else do we want to run in the Paravisor? If you notice here that our first Paravisor didn't do any of some of the more complicated things that I kind of talked about in the previous slide. So with that, we decided, okay, I think we're going to have this new project, right, where we are open source so that people can see it and trust it. And with that, we have what we're calling OpenHCL. This is a Rust-based Paravisor from the OpenVMM project. It's open source. We develop it in the open on GitHub. And crucially, it provides us a platform to not only do what we did with previous Paravisor, which to interrupt virtualization, kind of the minimal subset of things that we needed for a Paravisor to do, but can also do all of these new things, right? Like provide enhanced diagnostics. We can do device translation. We can do way more. And additionally, we also write it in Rust. We think Rust is really important to the security of system software. And I'll talk more about, our findings with Rust and how OpenHCL is different. Like I mentioned, OpenHCL is open source. You can find us on GitHub. We have some links up here. We develop it in the open on GitHub, and as part of the broader OpenVMM project, we have a Zulip. For those of you that are familiar with some other open source projects, Zulip is open source chat client, so we have a Zulip. We have a developer guide there, and you can see some Rust grade documentations. But really, find us on GitHub, talk to us on Zulip. We're happy to talk more there. Here's kind of a picture of OpenHCL. It's pretty broad. You'll notice that effectively it's a very similar model, right? Like we still have this confidential VM. We still have these different privilege levels. It's still running in a higher privilege level. But you may notice a few differences, right? Like we have a bunch of different components. Really, we use user mode and kernel mode here. This for reasons which I'll talk more about in upcoming slides. And we also have a small minimal Linux kernel, which allows us to do various things. But effectively, it's still Paravisor, right? It's providing services to the guests running in a lower privilege level that may have been harder to write in the guest OS itself. So what is kind of our design philosophy around OpenHCL? Well, you want to write as much code in user mode as possible, right? And when you think about the previous slide, that's why we have all these different user mode components. And this includes things like device drivers, virtual machine, virtualization, machine management code, VMM code, the different device emulators like VTPM, Serial, etc. We really want to write user mode code. And that's because we can then write a lot of safe idiomatic Rust wherever we can, right? We don't want to write unsafe Rust. If we did, we kind of defeated the point of writing the Paravisor in Rust in the first place. And so to do all that, we have this minimal Linux kernel, which gives us a very standard Rust environment. Talk a little bit more of that in future slides, but effectively, we have this pretty standard, pretty close to upstream Linux kernel that we have, a few extra patches on so that we can access the virtualization primitives that we need. But otherwise, it's just a pretty standard Rust, Linux Rust environment we can run our code in. And one other big design goal of the project is we want to keep all of this user mode code, like VMM code, device drivers, etc., as OS agnostic as possible. And why do we want to do that? Well, that allows us both a better development loop, right? Like you don't need to always develop in a specialized environment. You can just develop on a standard virtualization API for if I'm writing, say, some NVMe code or some other device emulators, right? I don't need to always run it in this specialized Paravisor environment. I can run it on a normal, VM using WHP or KVM. And that also allows us some flexibility about, looking and investigating at future runtimes we could even use for the Paravisor in the future, right? There are some other projects, probably the most notable one is the Coconut SVSM project. Now that is a very interesting idea that we could look towards in the future about using to host this Rust runtime environment for the Paravisor. And so we want to really keep that flexibility open, right? We want to keep ourselves honest so that we're not too tied to specific operating system and really able to run all this different user mode code in these different environments. So I want to talk about Rust. And when you think about where the Paravisor is in the guest, it's really a crucial component to the security of the guest. And we know how difficult it is from previous experience writing C and C++ code to get that code completely right. Especially when you start talking about performance and you start talking about doing offering more sophisticated services, that's more code complexity, and how do we maintain that our code is correct and that you don't have security issues, memory safety issues, etc. So we took a pretty we find Rust to be very important for that. And a big part of that is our ability to write safe Rust, not just unsafe Rust. And what you get with safe Rust is the borrow checker, the compiler. It helps you reason about the safety of your code and push a lot of those bugs that you would find later at runtime or in testing to compile time, right? Rust borrow checker lets us manage buffers and ownership in a way that you can't really do with C and C++. We can use lifetimes and references to avoid copies, especially since we have this I/O path in the Paravisor when we are relaying storage or networking. Performance is really important, and we want the Paravisor to be as performant as possible, but we also want it to be correct, right? We can't let the Paravisor compromise the safety of the guest. So all of these different parts of Rust, like borrow checker, different traits, the type system, these all allow us to write safe code where we are much more confident about the correctness of our code and that we're not writing vulnerabilities. And for those of you that are familiar with Rust, Rust has this way to write unsafe code. And this is a way to tell the compiler that, hey, I know what I'm talking about. I need you to trust me, the programmer, that I'm doing the right thing because I need to implement something that falls outside of Rust's normal safety rules. And so in our project, we take really, really great care to make sure we only limit unsafe code to what we absolutely need. So we limit to specific files, specific crates. Those are libraries in Rust terminology. And we really have a very small amount of unsafe code in the Paravisor. This is actually this 1,400 unsafe blocks is in the whole project, not just the Paravisor. But you can see we really limited unsafe code to really what we think is the absolute minimum of what we need. And that's great. That helps us, most developers don't need to worry about these additional rules around unsafe code and these additional safety guarantees you need to maintain. You can rely on the compiler and everything to verify the correctness and safety of your code. We also find that Rust is much more productive for us, right? Rust has a pretty standard build tooling and library ecosystem. Cargo is the standard build system. Crates.io is the standard place to get libraries. And this allows us to both incorporate upstream crates that are high quality. Zero copy and tracing are two really important crates that we use. But also for prototyping, we can say there's this crate that looks like it does what we need. We can go ahead and pull that in and we can decide later, okay, are we ready to accept that as a real dependency, or do we need to, vet it a little bit more, maybe contribute fixes back or write something else? Additionally, you get a lot of modern language features like the trait system, the type system, references, async. And we use all of these to really be a lot more productive than we have previously. And you get a lot more modern tooling with compiler, like I mentioned, and tools like Rust Analyzer, which I want to call out, which are super helpful when you're writing Rust code. And so we have all that, and Rust is also a systems language. This is writing a virtual machine manager. You need a lot of access to low-level systems. We need to we write device drivers in Rust. We can write VMM code in Rust. And we can even write Rust code that is what we call no standard, which runs not in an operating system. Not pictured here as the boot process, but we do have this no standard boot gem. And so Rust's power lets us write all of these. We don't need to use a different language. We don't need to write C. We can just write everything we want in Rust to get safety of the compiler, take advantage of the compiler, and it gives us the power to do what we need it to do. But we can also fall back to calling different OS APIs like C APIs if we need to, and even assembly. So we have that flexibility, and Rust gives us that flexibility. So I've talked a lot about safety and productivity, but obviously if Rust was not performant in this resource constrained environment, it wouldn't be successful for us. But Rust gives us the power to, gives us the performance that we need on top of all these safety guarantees, right? Think about where the Paravisor is running. It's not running on the host. It's running inside the guest. It's using the same memory that the guest is using. Any memory we use for the Paravisor is memory we can't give to the guest OS and the guest workload. Any CPU time we take is taken away from the guest workload. So we're heavily incentivized to keep the environment as lean and as fast as possible. And Rust allows us to really write that safe, high-performing code and do these complex things like, the performance we need to be on the I/O hop path without compromising on safety. For any of those that have written C and C++, it's very difficult to write correct C and C++ in a multi-threaded environment where performance is really important. One thing I just want to call out is, I won't talk about it more here, but we do use Rust async to give us even more flexibility around runtime with user mode scheduling, because we want to write as much of our code in user mode. And Rust as a language has given us the power to both be safe and performant, right? Which is ultimately what we want. So you might have noticed it's multiple slides ago that we use Linux. And why do we use Linux? Well, I just talked about why we want to write Rust, but crucially for Rust, we want to write standard Rust code. And what does that mean? That means that Rust has this concept of no standard and standard. Standard means you're running within the context of an operating system. You have access to file systems and threading, etc. Whereas no standard means you're a freestanding binary. You don't have an operating system that you can call for, say, networking or threading or synchronization. And the key point is that no standard Rust, while powerful, is difficult to code in. You don't have all these different services that an operating system would normally provide. So you kind of have to write it yourself. Rust as a language is still kind of stabilizing a lot of things around no standard. So we took a bet that, hey, we want to write standard Rust code. It's easier for the vast majority of developers, even in the operating system space, to write standard code. So Linux really gives us that ability to do that. And like I mentioned before, we want to write all of our code in user mode as possible, and this includes drivers. So Linux gives us a standard driver framework to do that. We can use VFIO to write user mode drivers for NVMe and networking. Additionally, Linux gives us, a pretty familiar OS platform for people, right? People know what Linux is. There's all kinds of tooling that's supported, like GDB server for debugging, perf for performance tracing. You can get a shell, etc. And also, it's broadly supported in the Rust ecosystem, right? If we were to go and write a whole bunch of no standard code or custom runtime environment, a bunch of crates that we want to use that are high quality crates may not support that well. And the key point is, stable toolchain support is also really important for us, since we want to make sure that we're not relying on nightly features and having to have these nightly toolchains to build the project. So that's OpenHCL. If you think about what we're looking at in the future, right, we want to support new architectures like ARM-CCA. Today we support SMP and TDX, but we want to make sure that we can run the Paravisor in multiple environments. We want to support reproducible builds. This is something we're looking at. There's a lot of work to get reproducible builds, but still something we're working on. We want to support other virtualization platforms, so you can run in this OpenHCL, not just on Hyper-V, but on other things. But thank you. Here's a link to the project again. I hope you found this talk useful.